Hello everyone. In this video, we continue our discussion on data structures. A data structure in Python is a way of organizing and storing data so that we can handle them efficiently. In particular, we talk about built-in data structures in Python, such as lists, tuples, sets, and dictionaries. And although these data structures provide a lot of flexibility, but in many machine learning and data science problems, we need to be able to store multidimensional arrays of data. So what does this mean? So let's say we have a data set where we have 1,000 houses in this data set, and each house has multiple features or attributes, such as the number of bedrooms, the square footage, etc. In this case, we cannot simply use a Python list because then we have to store multiple pieces of information for each house in our data set. What makes more sense is to have a two-dimensional array where one dimension corresponds to different houses that we have in our data set, and then the other dimension corresponds to features or attributes for each house. In order to implement this, we can use NumPy, which is a fundamental library for scientific computing and data science with Python. And the very special thing about NumPy is that it provides support for large multidimensional arrays, such as matrices, along with a collection of mathematical functions, random number generators that you see in probability and statistics, linear algebra routines, and a lot more. The fundamental data structure in NumPy is known as ndarray, which stands for n-dimensional array. Ndarrays can have multiple dimensions, allowing for the representation of matrices and higher dimensional versions of matrices, which we usually call them tensors. ndarrays are very memory efficient and faster than built-in Python lists, especially for large datasets. And this efficiency is crucial for numerical and scientific computing and in general for data science and machine learning problems. And the other thing that we need to consider here about the importance and significance of NumPy is that many other libraries in the Python ecosystem, such as pandas, scikit-learn, TensorFlow, they build upon NumPy. So this is about the dependencies between libraries and packages that we discussed in lecture 1, where we said that we need to have some sort of package manager, such as Conda or Anaconda distribution platform. But NumPy comes standard with Anaconda distribution. So if you have followed the instructions to install Jupyter Notebook and Anaconda distribution, you should be able to have access to NumPy. And very similar to math module that we used before, and we had to import math to be able to use math module. Here is the same thing. We first have to import NumPy. However, we can also make this a little bit shorter, this name, and we can import NumPy as, and here we assign the name NP as an abbreviation for NumPy. So this part is really optional. You can just import NumPy, and anywhere else here where we have NP, you just have to replace that with NumPy. But it is a good practice to use the abbreviated name, which is NP. And one way to make sure that you have NumPy and it's working well, very similar to what we did before with Python and Conda versions, is to see what version of NumPy you have. And we can do this here using this np.__version__. If I run this cell by using Shift-Enter or using run here, you can see that we have version 1.26.2. Okay, so that's great. It means that we have NumPy here. So as I said multiple times before, the nice thing about NumPy is that you can have multi-dimensional arrays. So what does this exactly mean? In this context, an axis represents a specific dimension along which the array or the data is defined. So this means that in this case, we have a one-dimensional array. This is very much like a Python list where you have these values stored across this one axis that we have. And remember that indexing in Python always starts with 0. So this means that this axis that we have is axis 0. And what is the shape of this array? Which means that we need to count the number of elements we have along each axis. So here we have one axis and we have 4 elements in it. So the shape is 4, comma, and these parentheses. And if you're wondering why we are using this, remember that if we use parentheses, this is what is known as the tuple, right? That's like one of the main data structures we covered in the previous lecture. And we said that in order to make sure that we have a tuple with a single element in it, you need to have the trailing comma that you can see here. So you can see now how all these different pieces of information that we have, they relate to each other. So the shape is a tuple that counts the number of elements along each axis. Here we have one axis, so we have one element, and we have the trailing comma to make sure that this is actually a tuple. One thing that is used very, very frequently in data science and machine learning problems is the 2D array. This is the example that I said about houses and the attributes and features that we have for each house, right? So in this case, you have a two-dimensional array, meaning that you have two axes. So axis 0 is this vertical one, and axis 1 is this horizontal one. And I really want you to remember, take a snapshot of this and remember this, the way that we index these axes that we have here, right? So axis 0 is this vertical one, and axis 1 is this horizontal one. So what is the shape here? So you can see that we have two elements along axis 0, right? 1, 2, and we have three elements along axis 1. So the shape is a tuple where we have 2 and 3, right? So in some sense, the length or len, length of this shape, gives you the number of axes that we have. And we can do the same thing with this three-dimensional array that now we have. So you can see that now we can expand what we know about these ndarrays, right? So we have axis 0, we have axis 1. So what we have in the front face here is exactly that 2D array, but now we can have this third axis, which is axis 2, and now we put together all these different two-dimensional arrays, and the overall structure is a three-dimensional array. So what does this mean, this evolution from 1D to 3D array? So let's say for 1D array that we have on the very left, you can have one house in your data set, and there are 4 features associated with that house, right? For example, the number of bedrooms, the number of bathrooms, square footage, etc. For the middle case, where we have a 2D array, you can have 2 houses in your data set. So that what that axis 0 corresponds to, right? This means that the first one you can see here is house number 1, and the second one is house number 2. And then the axis 1 corresponds to the features for each house. And in this case, because we have 3 elements, means that we have now 3 features for each house. What is the 3D array on the right side referred to here? And you can see in this case, you may have, let's say, 3 different regions in the United States, and each axis element in axis 2 corresponds to one region, right? And in each region, you have 2 houses with 3 attributes, right? So we can create these multi-dimensional arrays that can contain a lot of information about the houses in each region, and then how this expands to different regions in a country. And now we can also have a 4th axis here that can be like different countries, right? So you can see that we can create these multi-dimensional arrays that contain a lot of information, and we cannot typically do these types of data storage and handling using like Python lists or dictionaries, etc., that they are built in Python. Something else to keep in mind here is that the number of axes in an ndarray is referred to as its rank, right? So in the left array here, the 1D array, we have one axis, so it's rank of 1. And then the middle one is rank of 2. And the one on the right side is rank 3. And something that we can also practice here, since this is not included here, what is the shape of the 3D array that we have here? So you need to count the number of elements along each axis, right? So the shape is 2, 3, 3, right? So because we also have 3 elements along axis 2. So once you remember the way that we index these axes, it becomes very easy to find the shape of each array. And in particular, as I said, we really care about 2D arrays or matrices, right? In this case, the rows are the horizontal lines in the table, and the columns are like the vertical lines or columns that we have here. As you can see here, in this case, we have the first row, which is shown here. And then because we have these indices 1 through n for the rows or the first index here, we can see that we have n rows, right? So that's the last row, which is row number n. And then similarly, we can define the columns that we have here, right? So we have column 1 up to column m, which is the last column that we have here. So these rows and columns corresponds to axis 0 and axis 1 that we have there. And in this case, we call this matrix of size n by m because we have n rows and m columns. And we will talk about indexing these two-dimensional arrays, but you can already see now in order to retrieve each element here, we need two indices. One that shows that the row number and the other one the column number, right? And in a programming Python programming language, this means that we have to give the index for axis 0 and the index for axis 1, and we'll be able to retrieve the corresponding element. Okay, so now let's see how we can actually create numpy arrays in these cells that we have. So we're going to start with a one-dimensional numpy array using np.zeros. So what this does, it creates a one-dimensional array of all zeros with 4 elements in it. So if I run this, you can see that we have a one-dimensional array. So this looks very much like a Python list where you have 4 zeros here. And we know that this is a numpy array because it shows here array, right? So if it was as a Python list, we wouldn't get this array here. And as we said, for every numpy array, we have an attribute which is called shape. So if I say a.shape, you can see that we get 4, the trailing comma, and these parentheses, right? So this shows that we have one axis here, or the rank is 1. And remember, here we shouldn't use parentheses because shape is not a function or method here. It just gives some feature or attribute of this array. The same thing with this ndim attribute, which is the number of axes or rank. So if I run this, we get 1. And if you're not sure, you can always use the type function in Python, and it will tell you the type of the object that you have. And in this case, if we run this cell, you can see that we get numpy.ndarray. Okay, so now let's make this a little bit more complicated by looking at a 2D array, right? So in this case, I'm using np.zeros, but now I pass this tuple, right? So what this means is that now I want to create a 2D array of size 2 and 3, 2 elements along axis 0, 3 elements along axis 1. And this is exactly what we expect, right? There are a couple of things here. First of all, note that you have two parentheses here, two square brackets here. And what this means is that this is a 2D array. And then you can see that along axis 0, which is the vertical line that we have here, we have two elements. And then along axis 1, which is the horizontal one, we have 3 zeros. In other words, if I want to put this in the terminology that we had, this matrix has 2 rows and 3 columns, right? So this is a 2 by 3 matrix. And we can look at the shape attribute. You can see that now we have this tuple 2 and 3. And we can look at ndim, which gives us the rank or the number of axes, and we get 2. We can continue doing this with higher dimensional arrays, right? So in this case, we are creating a 3-dimensional array. And why is it 3-dimensional? Because we're using np.zeros. And then what we are passing here is 2, 3, and 3, right? So if I run this cell and print this numpy array b, you see that you get 3 square brackets here. So this is a sign that this is a 3-dimensional array. And the way that it works is that you can see that in the first element of axis 0, you have this 3 by 3 array. And then in the second element of axis 0, you have this 3 by 3 array. And now if you put this together, you get 2 of these 3 by 3 arrays, which means that it's 2 by 3 by 3. So once you get to 3-dimensional arrays and higher, you need to really practice a lot to make sure you understand the way that NumPy organizes these arrays. But you can see that with 2-dimensional arrays is much easier because we have the concept of rows and columns, and we don't have the third dimension. Okay, so moving on, now let's look at the shape of this array B, and you can see it's 2 by 3 by 3, and we can look at ndim, which is the number of axes, or rank, which is 3. And as we said before, one way to find this ndim method, which is the number of axes, is looking at the length of b.shape, right? Because if we count how many elements we have here, that's the number of axes. So you can see here that we can use also retrieve this information using the shape attribute. So far we have created arrays filled with zeros. Now let's create one filled with ones, right? So you can see here we have a 3 by 4 array. So we have 3 rows and 4 columns, and we have all elements 1. There are multiple ways to create NumPy arrays. For example, the other way to do this is using np.full. And what this does creates an nd array with a specified shape and fills it with a constant value. So let's say you want to create a 2 by 3 array filled with the constant value 7. So use np.full. And inside, the first argument, which is this one, is the shape, which is 2 by 3. And then the second argument is the constant that we want to use to fill this array, right? So in this case, we get this 2 by 3 array, and we have all 7s. The other thing that you can do is to actually have a Python list and convert or transform it to a NumPy array. In order to do this, you can use this np.array method or function. So in this case, use np.array and you pass a Python list. So in this case, our Python list is 143, and it's a Python list because we are using square brackets. And we pass this to this np.array, right? So in this case, if I run this, you can immediately see that it says array. So this is a NumPy array, but you can also use type if you want to. And you can see that it is indeed a NumPy nd array. If you look at the shape, you can see that the shape of this is 1, it's the rank of it is 1, but the shape of it is 3, comma, and these parentheses, because we have one axis, and in this one axis, we have 3 elements, right? But if you look at x.ndim, that's what was originally talking about, you get 1, right? Because we have one access, or the rank of this array is 1. Now, how can we create a 2D array using Python list? In order to do that, it's a very simple idea. You have to provide a list of lists. And what this means is that in this case, I have a list where the first element is another list, which is 2, 4, 5. And then the second element is another list, which is 9, 2, 7. So what this means is that if I create a numpy array using np.array, you actually now you get a 2D array where 2, 4, and 5 are placed in the first row, and then 9, 2, and 7 are placed in the second row of this array, right? And therefore, we have 2 rows and 3 columns. We can confirm this using what.shape, so you can see that we get 2 by 3, and we can look at ndim to find the number of axes, and we got 2. NumPy also comes with a lot of other useful ways of creating NumPy arrays, and one of them is this np.arange. So what np.arange does is that it creates an ND array with regularly spaced values within a specified range. So the syntax for np.arange, if you go to the documentation page of NumPy for this method or function, is that we have the start, a stop, and a step points. And obviously, we also have this other argument, which is d type, which is the data type. So this is if you want to, for example, create an integer, floating point numbers, etc. You can specify this. But the main part is this first part, that we have to have a start, a stop, and a step parameters. And if you look at it, for a start and a step, they are in these square brackets. And what this means is that these 2 parameters are optional, meaning that if we don't specify the starting point, by default is 0, right? Which is the first index or first location that we have in our array. You always have to provide the stop, because wherever we have to stop, right? In this case, you want to create regularly spaced values, so we can always start from 0, but it should stop at some point. So that's something you have to specify. And remember, very similar to the slicing technique that we mentioned, the stop is always exclusive, meaning that it is not included. And then for the step, the default value is 1. Right, so it's a very much similar to the slicing technique that we discussed in lecture 2. So let's see how this works, right? So I'm saying np.arange 10, and if we see what's inside z, so it's a numpy array because it has array here. It starts from 0 and it goes up to 9, right? So 10 is excluded. But what is cool here is that because it starts from 0, if you count, you actually have 10 elements here. Right, so from 0 to 9, we have 10 elements. But it starts from 0 and it goes to 9. Now, if you want only the even numbers from 0 to 10, obviously exclusive 10, then you can set the step size to be 2, right? So now you start at 0, you stop at 10, and the step size is 2, right? So 0, not 1, 2, 4, 6, 8. And then if you want to add 2 to 8, we get 10. And remember, 10 is exclusive. So that's where we have to stop at 8. And if you want to start at location other than 0, you just have to specify that, right? So here we say that we want to start at 1. And we want to go up to 5, exclusive 5, right? So you get 1 through 4. So that's one way of creating these evenly spaced values, or regularly spaced values, and this is very useful for indexing. But something else you can use is np.linspace. So np.linspace is kind of similar to that, but it creates a specified number of evenly spaced values over a specified range. And in this case, the main difference is that both endpoints are inclusive, meaning that np.linspace, what it means is that we want to go from 0 to 10, and we want to include both of them, and we want to have 5 equally spaced points. So if I run these, you can see that we get the 5 points that we want: 0, 2.5, 5, 7.5, and 10. And actually the length of each of these intervals, if you look at it, is 2.5. And the reason is that if you have like here 5 points, you actually have 4 intervals: 1, 2, 3, and 4. And then if you divide the entire length, which is here 10 minus 0 or 10, by 4, you get 2.5, right? So that's something to keep in mind here, that in this case, you get whatever number you mentioned here, like for example 5, you get 5 equally spaced points, and this means that now the number of intervals is always that number that you have there minus 1. But NumPy has a lot of really interesting applications. One of them is creating random numbers, right? That's something that we see a lot in probability, statistics, and obviously data science. And inside NumPy, we have a submodule which is called random. So the way that we can access these is np.random that provides functions for generating random numbers, right? And there are several key distributions that we really use them a lot in data science. One of them is uniform distribution, right? This is something you have in your calculators too, right? So you want to generate a uniform distribution in the interval from 0 to 1. And in order to do this, you can use np.random. And because we want the uniform distribution, we just use rand, and you specify the number of elements you want. So in this case, we get 5 random numbers from 0 to 1. And this is the distribution we have. So here you can, for example, make this 10. So in this case, you get 10 numbers, random numbers. You can make it 100. So you can see that now we have a larger list of or array of random numbers. But remember, still this is a one-dimensional array because we have one square bracket. It's just we cannot have all this information in one line. So you can see that it's in multiple lines. But other than that, it's really a one-dimensional array, meaning that everything is along one axis. So let's put this back to 5. It just makes it a little bit easier to see the output of this line. And then we have other distributions too, like normal or Gaussian distribution. And if you want to work with the standard normal distribution, and the standard means here the mean is 0 and the standard deviation is 1, you can just use np.random.randn. So you have this extra n here. And in this case, if I generate, let's say, 5 numbers, as you expect, because the mean is 0 and we have this standard deviation 1, we should get both positive and negative values, and we do get that, right? So you can see that we get 2 negative values. And something to remember is that every time you run this, because it's a random number generator and has a different seed, it gives you a different result. But overall, this is a random number, set of 5 random numbers coming from or sample from this standard normal distribution. Now, the nice thing is that you can also control a lot more about the parameters of these random numbers. So let's say instead of working with the standard normal distribution, you want to have the flexibility to change the mean and a standard deviation. And NumPy has already built-in ways of doing this. And instead of using randn, you can use normal. So np.random.normal, and you have multiple inputs that you have to provide here. This log or LOC is the mean of your distribution. Here we set it to be 10. A scale is the standard deviation. We set it to be 1. And the size, meaning that how many samples we have to draw from this distribution. So you can see that now, obviously, these numbers are closer to 10 as we expect, because that's the mean or average of this distribution. So you can see that now everything looks to be centered around 10. So we have a lot of nice ways of working with these. And like before, the most important thing is to look at the documentation page. So you can see that here is part of numpy.org, the official web page for NumPy. And if we click on this link here, you can see that here explains everything that we need to know about np.random.normal, right? So there are random samples from a normal Gaussian distribution. And if you look at the parameters here, you can see that it is mentioned that this LOC or log is the mean or center of the distribution. The scale is the standard deviation, and size is the output shape, right? So for example, you can give a tuple with 3 elements if you want a 3-dimensional array or whatever dimension that you're looking for. So we have a lot of options here. Now we can also have some discrete distributions, right? So if you want to have a uniform integer distribution, you can use np.random.randint, right? So that means that it's an integer distribution. And what happens here, you specify a range here. So this is the low number, this is the high number, and this is the size that you want to have for your output, right? So this says that we want to have a 2x5 array. So this is a matrix with 2 rows and 5 columns. And you want to fill these elements by a random number, which comes from a uniform integer distribution from 1 to 5, right? So that's what we can see here. I can, for example, change the number of rows to make this 3x5. And a quick experiment here, it shows that this 5 here is exclusive, right? Because I'm increasing the size of this array, and you can see that we never see 5, right? And this tells us that this starting point is inclusive and the stopping point is exclusive. Okay, so let's put this back 2 and 5 as it was before, and you can see every time I run this, we get different results. The other thing, for example, that in terms of discrete distributions is binomial distribution. So the way you can think of binomial distribution is that you repeat some experiment n times, and each time the probability of success is p. So in this case, each trial or experiment has binary outcome, meaning that it's either success or failure. And the probability for success on a single trial is p. And you want to find the probability mass function, which can be found using this formula. So in this case, if you want to have k successes, what you do is that you have this n choose k, so the number of ways that you can have k out of those n experiments or trials. So this is the combinatorial problem. And then you have to multiply this probability of success k times, because each time the probability is p. So that's where we get this exponentiation, p raised to the power of k. And because you only have 2 outcomes here, so the probability of failure is 1 minus p, right? Because you know that the sum of probabilities must equal 1. And in this case, you have 1 minus p raised to the power of the number of failures, which is n times k. So this is the probability mass function for a binomial distribution. But if you want to draw samples from binomial distribution, you really don't need to implement this from scratch, because you can just use np.random.binomial. And you provide the total number of trials or experiments, the probability of success, and then the size of the random array that you want to have. So if we run this, because the probability is greater than 0.5, this means that it is more likely to have more than 5 successes in these experiments. And you can see that we get 8, 7, 10, 5, 7, right? Because we do these random experiments 5 different times, and we can see that the first time we get 8 successes, and then 7, 10, 5, and 7. And we can obviously run this multiple times, so each time we get a different result based on the seed that you use. And that's what we have in the next cell here. So if you want to get reproducible results, meaning that still you have a random number generator, but a random number generator that gives you the exact same result every time you run it, and this is very useful in terms of reproducibility of your code, you can set the seed of the random number generator. And the way you can do this is using np.random.seed. And the number here doesn't matter. You can use 42 or any other number you want, but you can see that in this case, if I run this cell multiple times, then you can see that I'm running this again and again, you can see that we get the same exact result. But if I change the seed, this will be obviously changed, right? And in this case, I'm running this multiple times and I'm getting the same results. So this is something very helpful later on. If you want to make sure that your code is reproducible, you can set this seed value for the random number generator. The next thing we want to talk about is reshaping an array. So once we have an array, can we change its shape? And the question is yes. Altering the configuration of an ndarray is easily achieved by adjusting its shape attribute. But you have to make sure that the total size of the array must remain unchanged during this operation, right? So let's create these numbers from 0 to 11 using np.arange. Remember, 12 is not included, but we obviously have 12 numbers from 0 to 11. And in this case, this is a one-dimensional array, right? So if I just put, for example, a.shape, right, it's 12, and then the trailing comma, which means that this is a one-dimensional array. So now if you say that a.shape equals, so now you want to assign something to a 3 by 4, obviously we can't do this, right? Because for a 2D array of size 3 by 4, we have 12 elements, and we originally had 12 elements. So in this case, you can see that we get a 3 by 4 matrix. Great. And if I use ndim, the number of axes of the rank is 2, and the shape now is 3 by 4, right? So we assign a new value to this shape attribute, and this is a tuple. The other thing that you can do is to use the reshape function. So this literally does very, very much the same thing. And what it does, that's something important to remember, is that it creates a new ndarray, which is pointing to the same data. So remember that we said that whenever you have a variable, this information is stored somewhere in the computer's memory, and you're just assigning a label or container for that specific location. So when you're using this a.reshape 6 and 2, right? So obviously we have 6 rows and 2 columns. That's great. But remember that this b is referring to the same location in the memory. So what this means is that if I change a, for example, I change the element of a, where we have the first row and first column, and set that to be 20, right? So here I'm changing this element of a. Now we can see that we have 20 here. And if I check b, you can see that I also have 20 here, right? So this means that when I use that a.reshape here, we didn't create a completely separate copy of it. It's just the same data that we are referring to, but with different shapes. And in this case, if we change a, we are changing b as well. So that's something important to keep in mind. So the other thing also it's useful to know about reshaping is that in some cases you may have like a 2-dimensional array, 3-dimensional array, and you just want to simply create a 1-dimensional array, meaning that this is what is known as like flattening, meaning that you want to have a flattened view of your array where you have a 1D array. And in this case, you can use this dot rabble. And what this does, it takes b and make sure that now everything is flattened to have a 1-dimensional array, right? So you can see that 20 and 1, 2 and 3, 4 and 5, they all get put together in a 1-dimensional array along one axis, and then the last two elements are 10 and 11. So what is nice about NumPy is that, well, we have this very nice way of organizing data in terms of multi-dimensional arrays, but also we have a lot of interesting mathematical and statistical functions. For example, we can perform element-wise operations like np.power for exponentiation. In lecture 1, we talk about like comparison operators. When you have two, let's say, Python variables, we could compare them together. In this case, we usually have different arrays, right? So it's not just like one variable. We have multiple values included inside an array. And so np.equal, np.greater what they do, they provide comparison operators, but in a sort of like a multi-dimensional way where we can compare different values element-wise, right? So if you have two one-dimensional array and use np.equal, then you can see whether the first element of the first array is equal to the first element of the second array, and similarly, if the second element of the first array is equal to the second element of the second array, right? So that's how this works. You also have universal functions such as sine, cosine, hyperbolic sine, exponential, logarithm. This is actually NP, not NO. So you can see that we have all these universal functions. You can also find descriptive statistics, finding the mean or average, standard deviation, mean, max, percentile. So if you have any statistics courses, you're probably familiar with these different ways of finding descriptive statistics. Or in linear algebra, we can find dot product between vectors, or matrix inversion, matrix eigenvalue decomposition, etc. Right? So this linalg here stands for linear algebra. You get a lot of interesting linear algebra routines that you can use. And just to showcase you some of these, right now we don't want to go too much into these different topics, but let's say we create this one-dimensional array, which contains 2, 3, 8. You can use np.power, and then you pass the array that you have in 2. So this means that you want to raise each element to the power of 2, right? So we get 4, 9, and 8 squared, which is 64. And now if I have a second array, which contains these 3 elements, 2, 5, 6, now you can use np.equal and pass these 2 arrays. The first array, my array, and my array 2, and see whether they are equal or not. So this is an element-wise operation. 2 is equal to 2, so that's true, but that's not the case for the other 2 elements. So we get 1 true and 2 falses. And you can also use like np.grader, right? So in this case, we can see that only for the third element, 8 is greater than 6, but for the other elements, actually, it is false, right? Meaning that the first element of the first array is not greater than the first element of the second array. So a lot of this we covered before, but now we just can do this element-wise in a very efficient manner. And other thing that is very important, for example, let's say we have this my array, which is a 2D array, right? So the first row contains 1 and 2, the second row contains 3 and 4. We can find the mean or average of all the elements, right? That's what we call here overall mean. So if you add everything here, it should be 10, 1 plus 2 plus 3 plus 4, divide by 4, you get 2.45. But also, the cool thing about NumPy arrays is that it can calculate mean along a specific axis, right? So remember, axis 0 refers to the vertical axis, and that's where the columns of the matrix are, right? So this means that you want to find the mean or average column-wise. And if you do this, right, use np.mean and set axis equals to 0, you can see that we get 2 and 3, right? Why? Because the first column contains 1 and 3 here. And so that's 4 divided by 2, which is 2. And then 2 plus 4, which is 6, divided by 2, which is 3. And similarly, we can find the mean across the axis 1, and that's the horizontal axis, which means that these are the rows of this matrix. And in this case, if we run this, you can see that we get 1.5 and 3.5. And the reason is that 1 plus 2 is 3, so that's the first row. And divide by 2, we get 1.5. And then similarly for the second row, we get 3 plus 4, which is 7, divide by 2, which is 3.5. So you can practice this and see how these different axes, you can find the average or mean, maximum values, different descriptive statistics. But it is very nice to have this option of working along different axes. Some other operations that are more useful in terms of linear algebra routines is, for example, dot product or inner product. In this case, you have two vectors of the same length, and then the dot product, which we use this notation here, is simply the multiplication of element-wise multiplication, and then adding all these results of these multiplications, right? So A has n elements, B has n elements. You multiply the first element of A by the first element of B, and similarly the second element of A by the second element of B, and then you do these multiplications and add all of them together, and the result is a single number. So here you can see that we can test this by creating two 1D arrays. One is 1, 2, 3, and the other one 4, 5, 6. And the function that we have for this is np.dot, and then you pass the two arrays. So in this case, we get 32, which is it's like 4 plus 10 plus 18, right? And that gives us 32. Now, let's talk about matrix vector multiplication. That's something that we use a ton in machine learning and data science, right? That's something that, for example, when we talk about linear regression and its extensions, we always need matrix vector multiplication. And the good news is that we can do this very efficiently using NumPy. So recall that in this case, this matrix that we have here has m rows and n columns, which means that is m by n. And this vector in front of it has n elements, right? So in this case, if we perform the multiplication, we have different ways of doing this. One way is to take the first element that we have here and multiply this by the first column. And similarly, we multiply this last element here by the last column. And this would be the result of this matrix vector multiplication, right? So it would be an m-dimensional vector. And the other way to do this matrix vector multiplication is in the form of dot products, right? So in this case, we look at the rows of this matrix and we find the dot product that we just mentioned between these two one-dimensional arrays. And that's something that we can write in terms of this summation here, right? So you can see all of these elements, because during the first row, the first index is always 1. And then the second index shows you the column number. So here is I, and we multiply by xi. And I goes from 1 to n, right? So this is the mathematical definition of the dot product between these two 1D arrays. And we can repeat this until when we get to the last row, which is row index m. So you can see that these indices are all m. And we have, again, a summation from 1 to n of mix's. So we can perform matrix vector multiplication using either of these two formulas. But the nice thing is that this is already implemented in NumPy. And the way that we can do this is using np.max, which stands for matrix multiplication. Okay, so now what we're going to do is going to create a matrix A. So this is a two-dimensional array. And we know this because we have a list of lists. And then we have this X, which is a one-dimensional array because it's just one list with 3 elements in it. And if we do this matrix multiplication, you can see that we get 25 and 58, right? Just to show the shapes of these arrays, A is 2 by 3, and X is a one-dimensional array with 3 elements. So when you do matrix vector multiplication, this number and this number should be equal. Otherwise, we cannot do the multiplication. And the result is always this number by the number that we have after this trailing comma here. But in this case, you don't have anything. So that's why we just get a 1D array with 2 elements in it, right? And here we can also visualize what's inside A. So this is our A, which is 1, 2, 3, 4, 5, 6. And this is what we have in X. So one way to confirm what we have for matrix multiplication is to find the dot product between the first row and X and the second row and again X, right? And the way we can do this, again, using this indexing notation, right? So what this says is that we want to have the first row of A and all the elements that are in those columns. So we are not really indexing across columns. It's just we want to pick the first row and find the dot product or inner product between the first row and X. And similar here between the second row and X. And if you run this, you see that we get 25 and 58, which is the same as what we have here. So that's always something useful really to do to double check your analysis to make sure that you have not done anything wrong in the process. So now that we talk about selecting the first row of A, let's talk about, and the second row of A, let's talk about more in-depth about array indexing when we are working with these multi-dimensional arrays, right? So for one-dimensional arrays, we can access elements more or less like a Python list, right? Because it's basically a list, just, more efficient because we have all these built-in functions and methods, element-wise operations in NumPy, right? So in this case, we create a 1D array and we want to access the element at index 2. And remember that indexing starts from 0. So 0, 1, 2, right? So in this case, we get 3. And you can also use the slicing notation as before. This is the starting index and the stopping, which we don't specify, meaning that we want to go to the end of this NumPy array, which gives us 3, 4, and 5, basically these 3 elements. For two-dimensional arrays, where we have a matrix, you saw before too that each element that we have here needs 2 indices, right? Because we need to know where we are in the rows and in the columns, or where we are in axis 0, where we are in axis 1. So we need 2 indices, right? And in this case, let's create a 2-dimensional array of size 2 by 3. And what this means here in this case is that we want to pick element at row 1. Remember, the first one is row 0. This is row 1. And then column 0, column 1, column 2. So this is the element that we want to pick, right? And you can see that we get 6. And in the next cell, what we are doing, we're saying that we want all the rows. So we don't want to do any indexing across the rows. But for the columns, we want 1 through 3. And remember, this is always exclusive. So this means that column 1 and column 2 and all the rows. So you can see that we get this portion of the matrix 2 and 3, 5, and 6. So basically very much like what we had before, except that now we have to do indexing across both axes. When you're working with more than 2-dimensional arrays, something that is very useful is using ellipses, which is these 3 dots that you see here. And this is a convenient shorthand for representing multiple columns in an array slicing. And it is often used when you have, as I said, when you have arrays of more than 2 dimensions and you want to just specify a slice along a particular dimension, right? So let's create a 3-dimensional array. So you can see that we have 3 elements across axis 0, and then 4 elements axis 1, and 5 elements for axis 2. And in this case, let's say I just want to pick whatever I have in index 2 for axis 0, right? So again, now you need like 3 sets of indices, and the first one corresponds to axis 0, and I set that to be 2, right? So that should give me what we have here, right? Because this is what I have in the first element of axis 0, the second, and this is the third one, which is index 2. And if I run this, you can see that that is correct, right? So I get exactly what I have here. But then the problem was that I have to use colons, and you may have more dimensions or axes here. So one way to make this more professional is to just use these 3 dots, which is known as ellipses. And in this case, you can see that we get exactly the same result as before, and we don't have to specify that we want to select everything from all other axes that we have. The other important thing that we want to cover here is that for indexing NumPy arrays, you can also use Boolean indexing, right? So remember, Boolean values are true and false, and you can have Boolean arrays, meaning that arrays of true and false values. And you can use these to index or filter elements from an array. And this works as kind of like a mask, right? Where if you have true means that I want to pick something. If it's false means that I don't want to pick that element, right? So let's create a one-dimensional array with 5 elements in it. And then I create this mask for indexing where I have true, false, true, false, true. So this means that I want to pick the first, third, and the fifth element here. And we can do the indexing like before. We just pass this Boolean array, and you can see that we have the first, third, and fifth element here, right? So why is this useful? Because in many cases, you want to actually do some sort of conditioning, meaning that let's say I have an array of elements like what I have here, right? So we are doing some data analysis and we got a bunch of numbers, and you want to only keep elements that are above some threshold, and this threshold is 8 here. So what you do first, you create this mask, which is a Boolean array, and you say that array greater than threshold. So what this does, it creates a one-by-one sort of or element-wise operation to figure out whether each element is greater than 8 or not. So it will be a Boolean array of trues and falses. And now if you pass this to the array that you have originally, you will keep the ones that are actually greater than 8. Right? So you can see that in this case, we get 10 and 12. And you can easily see this by just looking at this mask, right? So you get true because yes, this is greater than 8, false, false, true, and false. And you use this for indexing, right? So when you're working with large arrays, you don't want to go and individually inspect them. You want to be able to pick the ones that, for example, are greater than some threshold, and you can really do this literally in one line of code, because what you can do, you can write this as the array, an array greater than threshold, right? So this can be written in only one line of code, and in this case, you get the result that you want. So it's a very compact way of doing indexing. The other thing we want to talk about here is concatenating NumPy arrays. And in order to do this, you can use np.concatenate, and the syntax or the grammar is that you provide this tuple of arrays, and then also you need to specify the axis along which you want to concatenate, right? So in this case, you can see that we have array 1, which is a 2-dimensional array, and array 2, which is another 2-dimensional array which has 5 and 6 in it, right? So you can see these arrays here. That's array 1 of size 2 by 2, and array 2 is 1 by 2. And now you want to concatenate these along axis 0. So what this means is that if you run this, you can see that we have the 1, 2, 3, 4, right? So that's the 2 by 2 array. And then the other 1 by 2 array now is concatenated. So the result is actually now 3 by 2, right? And we can confirm this too by looking at the shape attribute, which is 3 by 2. So this is very also handy if you want to have like concatenate or merge different data sets. You just need to make sure that you do it along the right or correct axis. And the last thing that we cover in this lecture is how to save and load arrays. Let's say you have done some data analysis, you have some NumPy arrays, and now you want to be able to store this information and load this information again. And one way to do this is using these two methods, np.saveText and np.loadText. right? And the way you can use it with the save text is that you need to provide the file name, right? What is the name of the file you want to store and the array that you have, right? So let's say here we do something very simple. We create a 2D array using Python list. And in this case, you can say that, well, I want to use np.saveText, and that's the name of the text file that we have, and you provide the array. And now use the np.loadText and just give the name of the file. And if you look at this loaded array, we can see that we were able to correctly and successfully load this array after saving it, right? So this is very helpful to make sure that the analysis you have done, you are able to store the result and be able to load the result later on, so you don't have to spend all the time again to redo your experiments. As before, we have 10 problems for homework 3, where we're going to extend on what we learned already in this lecture and do some practice and be able to really make sure that we truly understand the material covered here. In some of the cases here, you can see that I provided the documentation page for some of these NumPy methods, and this is just to make sure that you have the skills to be able to understand and read new read the documentation for new NumPy methods whenever you need them. Thank you for watching this video, and I hope you found this video useful.